Let's talk about the closed interval method. Okay, so the closed interval method allows us to locate absolute extrema. So absolute extrema, that just means absolute maximums and absolute minimums. All right. Now, we have a theorem that says if f is continuous on a closed bounded interval I, then f is going to have an absolute maximum and an absolute minimum that must occur at either critical values, critical points, let's call it, or at the endpoints. Okay, so the closed interval method basically just describes how to find these absolute extrema. So when we look at this, we could see, just to emphasize, uh, we want our function to be continuous, and our interval has to be a closed interval like that. And then there's a three-step process. So the first step you want to do is you want to find the values of f at the critical numbers of f in the interval AB. So that's the open interval because remember, critical numbers are interior points, so they don't occur at the endpoints. All right. The second thing you want to do is you want to find the values of f at the endpoints. All right. So now I have a bunch of values. I have at least two, possibly three or more, depending on how many critical numbers I have. Then the largest number, the largest value is the absolute maximum, and the smallest value, these are y values, right? So the smallest y value is the absolute minimum. Okay, so I figure I should show you an example. So let's take a look at example 2 over here. So for example 2, when we look at this example, the first thing I want to notice is I want you to notice that our function f is a polynomial, and we're working over this closed interval right here. So when I'm going to explicitly state, f is continuous since it's a polynomial. Now, I could show it's continuous in a different way. I could show it's continuous by calculating the derivative. So if I calculate the derivative, I'm going to get negative 2x plus 3. And this also shows that it's continuous. So this also shows f is continuous. All right. The next thing I want to do is I want to find the critical values. So I'm going to set this derivative equal to 0. So when I set this equal to 0, 0 is equal to negative 2x plus 3. That's the same thing as saying 2x is equal to 3, which is the same thing as saying x is equal to 3 halves. So now that I've found the critical values, I need to evaluate what is f of that critical value. I also want to evaluate f at each of the endpoints. So I'm going to calculate what f of 1 is going to be. And I'm also going to calculate what f of 3 is going to be. So you really want to make sure that you take these 3 points, that you plug them into the original function and not into the derivative. That's the way students usually mess this up. So I'm going to have negative 3 over 2 squared plus 3 times 3 plus 2. I'm going to have negative 1 squared plus 3 times 1 minus 2. And then I'm going to have negative 3 squared plus 3 times 3 minus 2. I'm going to take a second to pop these numbers into my calculator and see what those y values are going to be. So after popping these into my calculator, I get f of 3 halves is going to be 8.75. F of 1 is going to be 0. And f of 3 is going to be negative 2. So this tells me that my absolute maximum is 8.5. My absolute minimum is going to be negative 2. I want to make one final comment before we end this video. You need to make sure that you really need to make sure that when you find this critical value, we found this critical value of 3 halves. You want to make sure that this critical value is actually inside the interval that you're working with. So 3 halves is between 1 and 3, so we have no problem here. But sometimes you find critical values that are outside the interval. You don't really want to use that. You're really trying to find the absolute maximums and absolute minimums within a closed interval. All right, everyone, we'll do some classwork when we get together in class. Take care.